Hello everyone, this is Chris Wells, and this is the 0th video of 3 that will summarize and elaborate on some of the precalculus concepts that we went over in the class that I taught a couple of weeks ago. That class, to reiterate, was not a class that people got any official units or credits through the college, but instead was just an opportunity for people to refreshen up on some skills and to get ahead on some concepts, to gain a deeper understanding of the material as a whole so that it assists them in classes beyond precalculus, in classes like calculus 1, 2, 3, linear algebra, and differential equations, which are classes that everyone has to take if they want to be, a scientist, a mathematician, or an engineer. It is their future. So I wanted to offer people an opportunity to be more successful in how they understand the material. The first video, which is the next video, will go over what limits are. I will put the formal definition of a limit on the screen. I will also describe how to calculate limits, how to find limits, and some example problems that I will do. I will also have challenge problems. The way that challenge problems are going to work is that I will pose a few really difficult problems at the end that are about the topic that we just went over in that video. And then I will put the answers to those problems in the description so you don't see them immediately on the screen. Instead, it is just something to help people gauge and test themselves to see how well they understand it. The hope is that if you get a challenge problem correctly and you understand the problem, then you have gained a master level understanding of the subject. The second video is going to be about the number e. It's going to be an introduction to what the number e is, a intuitive financial perspective of what the number e is, and I will also describe the importance of the number e and the definition of one of the definitions of the number e. Again, there will be one or two challenge problems at the end of that video that will gauge your understanding of what the number e is and how we use it. And then the third video is all about the difference quotient. In my opinion, the difference quotient is the reason why precalculus is a thing. I treat precalculus as a way to get to and understand the difference quotient, and I will describe some effects of the difference quotient, such as the shortcuts for the derivative. I will derive the difference quotient and a few other things. Again, there will be a challenge problem or two at the end of the video. In this video, however, I'll kind of describe some of the things that are on the screen, not all of them. Some of this is for eye candy, but all of it is related to precalculus at some level. Only a few of these things are explicitly precalculus. But to begin with, I'd like to describe math in a more unconventional way. So in my opinion, I consider math to be a way that we communicate objective truths about things like quantity and speed and other such scientific and technological properties. So, how do we communicate? Well, as humans, there are several ways that we communicate. But in my opinion, I think that there are three very useful ways that we communicate. We communicate using our eyes, our ears, and our hands. So, algebra, in my opinion, the way that I'm going to be treating algebra in these next few videos is a way that we communicate math through our ears. It is a way of communicating math verbally through language. Trigonometry, I will be treating trig as a way of communicating math visually through our eyes. And then lastly, calculus is the way that we do math through our hands, the way that we write it, the way that we solve problems is typically through calculus or some variety or form of calculus. So to begin with, let's describe the first thing in order. So algebra is the first thing that we probably learn as a prerequisite to calculus. So these three things down here describe algebra. So these things are called conic sections. There are four varieties of conic sections. We got circles in yellow, ellipses in green, hyperbolas in blue, and parabolas in what looks to be like a red or orange, whatever. This thing on the right, that's a parabola. Now, A conic section is when you have a cone or multiple cones, one cone or multiple cones that are arranged like this, and you cut it with a knife, so to speak. This plane, this dashed line thing represents the knife. It represents the slice afterwards. And in this animation, the colors represent the slice. How you cut the slice determines what function or functions you're going to get. So on the left, we have a circle. The form of a circle is x squared plus y squared equals the radius squared. In green, we have an ellipse. The form of an ellipse is x squared over a squared plus y squared over b squared equals 1. And hyperbola, the form of a hyperbola is the same exact thing as an ellipse, but with a minus. So it's x squared over a squared minus y squared over b squared equals 1. And then the form of a parabola could be many things. In fact, actually, each and every one of these can be rearranged in a different way to get different things. But the easiest way for me to understand a parabola is ax squared plus bx plus c, the standard form, or one of the standard forms for a parabola. I will have these functions in the first video explicitly written as I said it, but I think that the geometric interpretation of a conic section, which are what these three animations are showing, is very important. Now, not in algebra, and you don't really do that in trigs, but it's not really powerful in algebra, it's not really powerful in precalculus, but man, these three things are very powerful in calculus 3. If you really know what a hyperboloid looks like, or an ellipsoid, or a paraboloid, you'll understand how to combine them. Such as an elliptical paraboloid. You'll know what that means and what that looks like if you understand what these four basic components look like individually. Again, precalculus is supposed to be an introduction to how you use math later. Trigonometrically, we have four things that represent something related to trig. We got this thing, we got this monstrosity, we got this thing, and we got this thing. So to begin with, this is showing the unit circle definition of sine and cosine. Now, there are three typical ways that we define sine, cosine, and tangent. I will just briefly describe them now. So the right triangle definition of sine, cosine, and tangent is a way of relating sides of a triangle in different ways. So the sine of theta is the length of the opposite side of the angle divided by the length of the hypotenuse. Cosine is similarly the length of the adjacent side to the angle divided by the length of the hypotenuse. And tangent of theta is equal to the length of the opposite side divided by the length of the adjacent side relative to the angle. It follows a mnemonic. It follows a mnemonic. So, ka, toa. Sine, opposite, hypotenuse. Cosine, adjacent, hypotenuse. Tangent, opposite, adjacent. It follows a mnemonic. There is also another way that we can define sine and cosine and tangent, and that's relative to a circle, not a triangle. So relative to the circle, which is what you see here, the green dot, the x-coordinate of that green dot, is represented by the cosine of theta, and the y-coordinate of the green dot is represented by the sine of theta. And then, if we go back to the right triangle, we'll better understand the unit circle definition for tangent. So on a right triangle, we can call sine, cosine, and tangent ratios. So we can say that the sine is a ratio between opposite and hypotenuse. We can say that the cosine is a ratio between adjacent and hypotenuse. And we can say that the tangent is a ratio between opposite and adjacent. But on a unit circle, we don't have opposites and adjacents and hypotenuses. We have x's and y's and radii. So opposite is really just y, adjacent is really just x, and radius is really just the hypotenuse. So in reality, tangent to theta is the ratio between y and x, otherwise known as the slope. So I like to think of tangent to theta as the slope of this green line at that angle. Now, up here, this monstrosity describes a whole bunch of trig functions and their unit circle definitions. But before I go into there, I'd like to describe the function definition of sine, cosine, and tangent. So all three of them are functions or can be represented as functions. The sine function takes angles as inputs and outputs vertical portions, vertical pieces. And the cosine function takes angles as inputs and outputs horizontal portions. And then, of course, tangent inputs angles and outputs slopes between those portions. But on the screen, we have the unit circle definition of several trigonometric functions. Now, please don't be scared. None of those, except for sine, cosine, and tangent, are used extensively in calculus. In fact, I have never used the varsign, which is green, light green. I've never used the varsign, or the x cosecant, or the covarsign, or the x secant. I've never used those in calculus, so don't worry. Those are not going to be there. But what you do use is sine, cosine, and tangent, and you also use chord and arc, but in a different way. So if I wanted to find the chord of theta, I would not use the trig definition because that's awful. Instead, I would use the algebra and calculus definition, which is going to be the distance between A and D. And then tangent, arc, the arc of theta, instead of using the, again, horrible trigonometric definition of arc of theta, I'm going to use the S equals R theta definition. So trigonometry, again, is the way that we communicate math visually. So that's everything you see on the screen is some sort of trigonometry attached to it, whether it's obvious or not. Some sort of way to describe it trigonometrically because it is a visual interpretation. This thing right here is a way that we can describe polygons in terms of sine and cosine. Notice that this right here is the same animation as one of these two. It's up to you to decide which one it represents. There is a right answer. You can write one in terms of the other, but this explicitly represents either sine or cosine. Just try and think of which one it represents. But notice that this has 4 sides and this has 6 sides. And if I put, a 10-sided or a 12-sided or a 15-sided or a 1024-sided or a 4096-sided or whatever, it's going to look closer. It's going to look more rounded. In fact, actually, a polygon with an infinite amount of sides or an infinite gon is a circle, or you could think of it as a circle. So using all of these, notice that this is showing an approximation of the area underneath this curve, and this is showing a way of approximating the curvature of a sphere, and this is, again, showing the approximations. And all these, everything on the screen is some approximation of areas or volumes or portions. And that's what calculus is all about. It's a way of turning approximation into reality. And precalculus gives you the tools to be able to do that. So with this thought, I'd like to leave you with this thought. Precalculus is not supposed to be just a prerequisite, but instead is supposed to be a stepping stone into better understanding single variable calculus and multivariable calculus as a whole.